Okay, so what we're going to cover with our little bit of time we have here is estimating the fugacity, partial fugacity in mixtures. So partial fugacity in mixtures. So for example, if we were to do, let's say, liquid-liquid equilibrium, which is what we're going to start off with. Well, eventually we're going to talk about gases for a second here. If we're going to start off with liquid-liquid equilibrium, we know how to solve for the properties of a pure liquid. If we have an equation of state, we have to just condense it and then figure out what the properties are, or we can look it up in a table. But if we want to do the phase equilibrium, we have one governing equation, right? The partial fugacity of I in phase 1 is equal to the partial fugacity of I in phase 2. That is the equation, or the set of equations, that we have to satisfy to know what is the composition of a pair of immiscible fluids. You'll have two phases with two materials, so ultimately you'll have about 4 equations you have to solve simultaneously. So all we need now is what do we put in for these terms here? That's really the question that we're trying to answer. If we're going to vapor-liquid equilibrium, which, truth be told, is what a majority of our phase equilibrium is going to be focusing on, we have to satisfy the relationship that for every component in the system, F over bar of I for the liquid phase has to be equal to the partial fugacity of species I for the vapor phase. So you can see we're going to have different strategies for estimating the partial fugacity of a liquid compared to the partial fugacity of a vapor. And so what we're going to be talking about is what are the assumptions and strategies that we can employ in order to estimate these partial fugacities. Because then once we have the equations derived, it's really just a matter of solving it for xi of whatever particular phase is, right? That's our goal. We want to know what the composition is of every species across every different phase. The more phases you have, the more complex it gets. The more species you have, the more complex it gets. The more non-ideal it is, the more complex it gets. Right? So at this point right now, we have a number of different pathways where we can step off at any individual point. Do we want to say it's a real fluid? Do we want to say it's an ideal mixture? Do we want to say it's a real mixture of real fluids? Right? There's all these different assumptions that we can make, but ultimately, this is the goal that we're trying to satisfy here. Can we match the partial molar fugacities? And with this, then we know that the system is in equilibrium. Now, for vapors, we're going to talk about vapors first. If we assume that it's ideal, that means that the volume of the species I in the mixture is same with the volume of it as a pure species. We can simplify our fugacity expressions quite readily. So our fugacity is more or less defined given by this formula here, our partial molar fugacity rather. So what we have is that the fugacity of species I in a mixture, which is given by this numerator term, right, is related to a scaled version of the pure fugacity based on its deviation going from ideal gas behavior, P equals 0, to real fluid behavior at some elevated P. Now, if we substitute in our approximation here, right, and we assume that the partial molar volume doesn't change when you mix it, then this term conveniently goes to 0. The logarithm of 0, the exponent of 0 is 1, which means that we can rewrite this expression so that the partial fugacity of species I is just equal to the scaled version of its pure fugacity. And we call this the Lewis-Randall rule. Now, one nomenclature change that we're going to stick to for basically the rest of the classical thermodynamics is that we are no longer going to be using xi for the mole fraction exclusively. We're going to write it more like this. F over bar of I is equal to yi f of I. And this is vapor mole fraction. So a nomenclature change here. X of i's are going to refer to liquids. Y of i's are going to refer to vapors. And that's because vapor-liquid equilibrium is so incredibly critical to most of the separations that chemical engineers do that we have adopted this fairly strict nomenclature. And so then the X of I is liquid mole fraction. Right, we do vapor-liquid equilibrium so frequently that it's just more convenient to come up with a new nomenclature system for liquids and vapors. Okay. So if we have an equation of state, so we're going to talk about the equation of state method. To get the partial fugacity. Now, this approach is going to be good for simple fluid mixtures, hydrocarbon mixtures, more or less things like hydrocarbons, things that don't have a really strong polar interactions. So if we look at one of the formulas of many, right, there's a ton of different ways that we can rewrite all of these expressions here. Right, this is a formula that we can use to calculate the partial molar fugacity from an equation of state. Now, it looks kind of similar to how we calculated the pure species fugacity. Right? We have a term right here that corresponds to ideal gas behavior. And then normally we would have a slightly different term, but now that we have a mixing system, we have a slightly odd-looking term, right, where we have dpdni. And usually we have something like dpdt or dtbdv in this location. Right? And that's more or less what we evaluated kind of on the exam and also for calculating the fugacity of a van der Waals fluid. So what we need is that for a mixture, how do we evaluate dpdni? Right, we need to know not only, right, how does a pure fluid behave, but how does a mixture of gas molecules behave, and can we manipulate our equation of state to somehow interject information on whether or not there's more moles of N1 or N2 or N3 or N4. So we need to restructure the equation of state in a form that we actually have some dependence on the composition of the system, right? Because everything that we've done so far, there's no dependence in the composition of the system. So to start off with, yeah, question?
I just have a question. That in the term above, is that your total molar, or total amount of moles? Or?
Yes, it'll be total number of moles, yeah.
Okay.
And if we look at the units really quickly, just a good double check here, right? The units of this here should be units of pressure, right? Because P equals RT over V. So this has to be units of pressure as well, right? And so that this N here cancels with this N there in the units. So you eliminate the molar term. So unit-wise, yes, that checks out as a quick double check. So we're going to start off with the Virial equation of state. Right, we can rewrite it as Z is equal to Z of the mixture, which is equal to PV PV over RT, which is equal to 1 plus B of the mixture right, so normally when we saw the Virial equation of state before, it was just B as a function of T. But now we've changed it so that it's B as a function of the temperature and of the composition of the fluid. So if we assume, if we have gas molecules in the system here, right, let's say two different types of gas molecules. If we assume that the total energy of the system is merely a summation of all of the different binary pairs of molecules that exist, and I'm not going to draw all of them necessarily, right? If we assume that the total energy of the system is only dependent on pairwise additivity, which is what the assumption is called, then we can write that the B of the mixture, right, and this is from statistical mechanics, that's where the Virial equation of state is derived from, it can be written as summation of I equals 1, summation of J equals 1, it can be written by this form here. Now recall, right, that in the equation to calculate the partial molar fugacity, we had to take the partial derivative of pressure with respect to n of I, right, the number of moles of species I, of species J, and so on and so forth. But this is given in terms of mole fraction, right? Those are not interchangeable. Right? You have to rewrite this expression in terms of n's, of the number of moles. Now this term Bij, now the book doesn't exactly use this terminology. I like to think of it as a type of binary interaction parameter. And what it does is it quantifies the attractive or repulsive interactions between molecules of type I and molecules of type J. And just for clarity, Bij is equal to Bji, right? It's symmetric, right? How molecules of type A and B interact is exactly the same as how molecules of type B and A interact. So if we have some sort of a basic, fundamental way to assess and understand how, let's say, water and, I don't know, ethanol in the vapor phase are attractive or repulsive as a function of temperature, right, or as a function of what other system conditions there are, we can then sort of predictively estimate how it might behave. In the real world, this term right here is more or less used as a tunable parameter to get the equation of state to fit for most mixtures. But the goal of StatMech or molecular simulations is obviously to say, look, I know what the molecular bonding of this particular system is. And if I know what the density of the fluid is, I know how many interactions there are, right? Can I somehow develop some sort of a theory where I can predictively assess how this is going to behave? Now, this is not all that important if we're talking about distillation of hydrocarbons, right? Because we have very good tuned equation of states, right? Before computers were super fast and powerful, where people just sat in the lab, did a bunch of distillation curves, fitted all these equations of state, and we've got some pretty good accurate models. But let's say, for example, as researchers, we want to come up with a new molecule that we don't know how it's going to behave. And let's say we don't know how to separate this expensive, valuable biomolecule, right? Then we're definitely going to want to have a way to be able to predict its properties, right? So there's a definite benefit to being able to understand these advanced molecular theories, but it's for modern, new compounds that we're going to develop, as opposed to, you know, how do we distill propane from ethane? I mean, that's not going to be a huge challenge. We've been doing that for almost 100 years, probably over 100 years. So anyway, so if we take this expression for the binary mixture and we substitute it back into that equation, work through all the mathematics, we can come up with an equation for the partial fugacity of a virial equation of state fluid. And notice that I've drawn the y, right? So the partial fugacity is a function of temperature, pressure, and vapor composition. The virial equation of state cannot predict liquids, so there's no reason to use a more general nomenclature here. Strictly speaking, this is just a plug and chug type problem. But the math gets to be increasingly more complex. Right? Because effectively what we've done is we've taken a partial derivative with respect to the number of moles of species I, but within that expression for pressure, we have an infinite summation, called double infinite summation. Right? So strictly speaking, it's plug and chug, but the math itself becomes significantly more tedious and more complex. Now, if we expand this to a cubic equation of state, and we are going to start off with the van der Waals equation. Right? Now we have double the problem. We have a term B, and we have the term A. So remind me, what is B quantifying? Excluded volume, and A is quantifying interactions. So which one do we think is going to be easier to estimate for a mixture?
I'm guessing excluded just because you can pick the size of the molecule.
Bingo. So what we're going to do is what they call one fluid mixing rules. So we're going to take the equation of state as it's written, and we're going to calculate effective properties for A and B of the mixture. So for B of the mixture, you guys correctly predicted that it should be the easier of the two to predict. This is just going to be an average value, which makes a lot of sense kind of conceptually. I don't think we need to overcomplicate this particular one. Right? If the B term quantifies how much volume is not accessible to the gases because it's a dense fluid, well, let's just take an average of the molecule size and call it good. That one makes total sense. Now for the A of the mixture, basically we're just going to beg, borrow, and steal from StatMech. We're going to say, look, if it works good enough for the virial equation of state, it's good enough for the cubic equation of state. And so we're going to use a form that looks almost identical. So what we're doing in this formulation here, right, and there is a vast amount of literature of what are the best mixing rules. And to a large extent, they are empirically derived. These are called the one fluid mixing rules, which means we're going to try and use exactly the same formulation of the cubic equation of state and just calculate effective properties based on the mixture composition. So this Aij term right here, right, which is necessary to quantify the interactions, we're going to say it's a property of the pure species interactions, right? The AII is how species I interacts with species I. The AJJ is how the species J interacts with species J. More or less saying, okay, let's say I have a noble gas that has virtually no deviation from ideality. Well, then it makes a lot of sense that if I mix it with something that really wants to interact, well, the noble gas is still probably not going to interact with it. But then we add in this additional binary interaction parameter that quantifies, okay, to what extent do these two things, exchange information? Are they attracted? Are they repulsed? What exactly is going on here? And then effectively what we're doing is now we're introducing the composition of the mixture into the equation of state. But this is, of course, one of many different type of mixing rules. But the main thing to remember is that all of these mixing rules have some degree of a theoretical foundation. They're not completely arbitrarily constructed. But at the end of the day, for most practical purposes, they're empirically fit. Exactly the same thing as a cubic equation of state. Right? There's a lot of thought process that went into this. It's not just a totally arbitrary construction of a function, right? This term here with the B mixing, yeah, it makes a lot of sense that gas molecules can't occupy all space, especially if it's a dense fluid. We should account for that somehow. How do we do it? We call it the excluded volume. It's the B term. This term over here, there should be interactions between the molecules. How do we best quantify that? Well, what they're saying is that the extent of the interactions will increase as the density goes up. That seems like a really good way to quantify it, right? Now, this form right here is very similar to the virial equation of state, right? But the virial equation of state is less of a function of the density, whereas a cubic equation of state is a much stronger function of the density. And as it turns out, you need this stronger functionality if you ever want to predict an unstable fluid that undergoes a phase transition. Right? So even though the cubic equation of state is, to many extents, right, it is empirically derived, it has a strong theoretical foundation which narrows down the type of functions that they'll consider. Same thing with the mixing rules here. Right? We're narrowing down the number of functions that we'll consider based on some theoretical foundation. But the final application of it is dependent on some sort of a tunable parameter that will be modeled or fit after classes of molecules, or if a lot of money's on the line, you'll actually tune it for the specific systems of interest, let's say in an industrial setting. Okay, so we ran out of time to talk about this, but we're going to continue on Friday, if everyone has energy after the fluids exam, to talk a little bit more about estimating partial fugacities. All right. See you guys at the end of the week.